In this part, we'll cover two main topics: experimental design and analysis of variance, and the second topic, regression analysis. This is a very popular statement by Box. So it basically says if the data is collected in a well planned way for any experiment, then even elementary methods of analysis can be employed. So by doing simple charts or simple tables, you can figure out what's going on. But conversely, even the most sophisticated statistical analysis cannot salvage a badly designed experiment. So it's very important that the experiment from which data are collected are designed properly so that we are able to extract meaningful information from those experiments. Now, what is a design of experiment? So it is also called DOE. It's a planned set of experiments or tests on the response variable. So there is a variable y variable which is the response variable. So there could be one or more than one with one or more inputs are also called factors, each at two or more settings or levels. Now just to give you an example, so this is an experiment where a manufacturer of cereal is considering three alternative box colors. So in this experiment, color of the box is a factor or a variable, and these three colors are the levels. To check effect on sale, 16 stores of approximately equal size are chosen. Red sent to 6, yellow to 5, and blue to 5. Following results in tens of boxes are obtained. So these numbers mean how many boxes were sold. So for example, 430 for the red because this is in tens of boxes, 520 and so on. Set of tests on the response variables. So we have y in that example where y is how many boxes were sold. So there was only one input factor which is color of the box, and then the number of settings or levels in that case were three, those three colors. So the idea is to determine if any factor or combination of factors is significant. So we want to know if it plays any role or not, because if it does not play a role, for example in this case, if color of the box does not play any role in the sale of the box, then why not have everything of the same color? So you can reduce cost by having all the boxes have same color. But in case it is found that the color has significant impact on the sale of the boxes, and let's say blue boxes are sold more than any other box, then we want to make more boxes with blue color so that the company can benefit by selling those boxes. And then we also develop sometimes prediction equations. So what will happen, like how many sales we can get if we send so many boxes. So we should be able to predict that by having some equations based on the data. And it also allows efficient optimization, so we can optimize a process. So in this case, this is an agricultural experiment designed to assess differences in yields of corn for four different varieties using three different fertilizers, so 1, 2 and 3. So now you have variety and fertilizer as two factors or variables. So this is one of the factors and this is another factor. Now this first factor, variety, has four levels, A, B, C, D. Similarly, second factor, fertilizer, has three levels, 1, 2 and 3. And the Y variable, which is the outcome or the response variable in this case, is how much was produced. So design of experiment can also allow efficient optimization. So you can choose what variety of seed and what fertilizer will be giving us optimal outcome. So design of experiments have several objectives. One is learning the most from as few runs as possible. So efficiency is the key for any good design of experiments because if you run an experiment, there will be some cost associated with that. Each trial will cost something. So we want to learn most from as few runs as possible. So we want to conduct minimum number of tests to get information that we need. Identifying which factors affect mean, variation, or both or none. That is very important because if a factor does not have any impact either on mean or variation, then that gives a clue that we can reduce the cost by not monitoring that variable very strictly. We can reduce the controls, maybe we can collect less data on that variable and we can reduce cost. But if we find that a factor is very, very important and it has a significant impact on the average or the variation or both, so then we have identified a variable that should be closely monitored and we can maybe make use of that variable to get the response that we need. It also helps to screen a large number of factors down to vital few. Sometimes you may come across a situation where you have too many variables. Now, when you increase the number of factors or variables in any experiment, then the number of experiments also go up drastically. So having more variables or factors will cause large experiments which are very, very expensive. So sometimes we are able to screen those factors and come down to vital few. So suppose you have like 20 different factors. If we are able to screen down from 20 to maybe only 5, then obviously that will bring down the cost. Modeling the process with prediction equations. So once we conduct the experiment, we can develop some equations and use that for making predictions. Like what if we change the temperature from this to this? What if we change the pressure from this to this? So what will happen to the yield? So such predictions are possible after we have data from the experiments. Optimizing the factor levels for desired response. So we can choose the proper values for those factors. So what should be the correct temperature be in a production run, or what should be the pressure be? What should be the speed with which the process is run? So all that can be obtained. Validating the results through confirmation. So experiments also may do some prediction and then we may have to run experiments and validate those outcomes. There are 7 steps for design of experiment. First one is to define project. So it is not necessary that each and every problem that a business faces can be solved by making use of design of experiment. So there could be some problems that are not suitable for design of experiment, or you don't need design of experiments to solve them. So we have to define a project first of all, and then make sure that whatever project is chosen is something which will benefit from design of experiments. And then we set up a team which is mostly cross-functional, because generally you need experiments when you have difficult problems and a problem that needs contribution from not just one department but several departments. So you may have a team which consists of people from production, marketing, sales, and so on. And then we have to state an objective, like what exactly we want to achieve from this experiment. Then we establish control factors and levels. So we have to identify what variables we can choose and what should be their levels. And then select response variable and the measurement method. Choose the experimental design. It means how many runs we have to make, how the levels of the factors will be changed. Are we going to have any replication? Do we repeat the experiment? How we are going to ensure randomization? and also local control principles. So how do we make sure that the outcome we get provide insight that we are looking for? So replication, randomization, and local control, these are three important principles that should be adopted. So out of 7 steps, you see 4 steps belong to planning the experiment. So planning is very, very critical, and that's why a lot of time is spent on proper planning of the experiment. Then only we move to performing the experiment. So if the plan is proper and it has been done very carefully, then conducting the experiment, this step will move very smoothly. So once we conduct the experiment and generate data, then the data has to be analyzed. So we analyze data and then we determine optimum levels of the factors. So because we have been changing the values of the factor, like temperature, we may be trying 3 different levels. Then we find out based on the data and analysis what is the best temperature we should use going forward and predict performance under these levels. So not only we identify what should be the best levels for the factors, we also predict what we are going to get by running those factors at those values. And then in step number 5, we conduct the verification. So we run a confirmation experiment and make sure that what was predicted is being achieved, and then we plan future actions. So let's look at another example. Wax is basically a factor, and type 1, type 2, type 3 are the 3 levels. So in this situation, your factor is Carvax, and the treatments or the levels are the 3 types, and experimental unit is CARS on which they were applied, and what we are looking at is response variable, which is number of washes. This is the data that is generated from these experiments. So it was run like 5 times each, and this number indicates how long they lasted. For each wax type, we see the numbers vary. It's not that we get exactly same number. So the key question is there any difference between type 1 and type 2 or type 2 and type 3? So we set up a hypothesis or a statement. So H0 is null hypothesis. So we assume that all the 3 waxes are equal. So mu1 means average from wax 1, mu2 means average from wax 2, and similarly mu3 is average from wax 3. So we assume all 3 are equal versus HA, not all the means are equal. So if some of the wax types or any wax type out of the 3 is totally different or gives a totally different performance, then HA will be correct. But if there is no difference, if there is no statistical difference among the 3 types of waxes, then H0 will be correct. So only one of the two can happen. It cannot happen that both HO and HA will be correct. So how do we know which one is right? So for that we have to do analysis of variance. So for doing analysis of variance, I would suggest you use Excel. So to analyze this, we can make use of a tool in Excel called data analysis. So if you click on data, you will see data analysis here. But if you have not done this in the past, then you have to first add this. And for that, you go to data and then options and go to add in. So we go there and you have to select first two and say OK. And then if you click on data, you will see data analysis in case it was not there. I will select the data I want to analyze and click on data analysis. So the first thing you see is ANOVA single factor. So single factor is just one variable or one factor. So because we have only one factor, which is wax, and it has like 3 levels, type 1, type 2, type 3. So we go with single factor and say OK. So input range, so this is our input range, and our data is grouped by columns, so that's true. Labels in the first row, so if you have titles in the first row like T1, then we check this box. And alpha default is 0.05, which means confidence level is 95% or 0.95. So I think that's okay. And then we can say we want our output to appear somewhere below this table. And then okay. So as soon as you do that, your analysis of variance table is ready. So this small table at the top, it only summarizes like how many data points were there for type 1 VAX, 5 each. What was the total number in that column? What was the average? So if you look at the average for first VAX, it is 29. So car is able to withstand 29 washes on an average. Type 2 looks better than this because this wax can last for 30.4 car washes on an average, and third one about 30 washes. So we see some difference in the averages, but are these differences statistically significant? We don't know till we do analysis of variance, because averages generally will be different, but we need to figure out taking into account variability. So in this case, variance for the first one is 2.5, third one 2.5, and for second wax shows slightly more variation. The ANOVA table here is given, and the first column is source of variation. So if you look at this data, we see that there is a lot of variation. Not all these numbers are exactly same. And you can see variation is anywhere from 27 to 31 or 32. So there is variation. So ANOVA table basically breaks down the variation into two types. One is between group variation and other is within group variation. So what is between group variation? So this is one group here, then this is the second group, and this is the third group. So between group variation captures the variation due to type 1 wax or type 2 wax or type 3 wax. The second one is within group variation. So if you look at just one group here, you can say it varies from 27 to 31. So that variation is captured in within group variation. So in statistics, generally this type of variation we also call error, because we cannot pinpoint and say why for this car the number of washes was 27, but same wax was applied to this car, it went up to 30. So what is the reason? So we cannot pinpoint and say why that variation is coming. But if somebody says that first type of wax has given an average of 29, whereas second type of wax has given average of 30.4. Now why there is a variation from 29 to 30.4? Then we can say this is because of a different type of wax. So a different type of wax was applied to the second group of cars. So that can be explained. So the explained part of the variation goes here between groups, and unexplained or error goes to within groups. So these two together form the total variability. So this column is SS, which stands for sum of squares. So sum of squares is calculated from the data, and the total sum of squares you can find is 38.4. This column is degrees of freedom. Degrees of freedom is calculated as, for between groups you have to see how many groups exist. So we have only three groups, three types of waxes. So 3 minus 1 is 2. So degree of freedom is 3 minus 1, that becomes 2. And generally then you look at total degrees of freedom, which is, you have to look at how many data points you have. So you have 5 plus 5, 10 plus 5, 15. So 15 minus 1 is 14, which is the total degrees of freedom. And then you can calculate within group degree of freedom as 14 minus 2, so it becomes 12. Next column is mean square. This column you calculate by dividing this column by this column. So if this is, say, column 2 and this is column 3, then this column equals column 2 divided by column 3. So 5.2 divided by 2 is 2.6. 33.2 divided by 12 is 2.7, and we don't do anything here. So you have only two numbers. And then to get F ratio, now F stands for Fisher. You divide 2.6 by this number. So basically we are dividing the mean square coming due to the effect of the three types of waxes. We are dividing it by the variability that we get within the groups, which is basically error. So if the variability due to effect of these three types of wax is less than the error, that means that wax is playing no role. Whereas if you get a situation where the variability due to the wax is higher than what is coming because of error, then we would conclude that the wax have significant role to play on the outcome. Obviously, F ratio you are looking at should be more than 1 if it is meaningful. Like in this case, you get less than 1. That means whatever wax you are using are not really playing any role. They are not affecting the response in any way. So that means there's no difference among the three waxes. You can also judge that by looking at the p-value. So p-value you can interpret by taking 1 minus. So equals 1 minus this p-value is roughly 0.58, or we can say 58%, roughly 58%. So 1 minus p-value is the confidence. So if you conclude that the wax has significant impact on the outcome or the response, then your confidence level will be 58%, which is too low. Generally, we look for a confidence level of 90% or 95% or 99%. So this is too low to really conclude that wax is playing any role. So in this ANOVA table, obviously this is a very, very important number. So if this number indicates a very low level of confidence, that means that variable is not important. So in this case, this is true, that there is no difference between the three type of waxes. That makes things easier. Maybe you can choose any wax. Maybe you can choose a wax which has minimum cost. And the analysis that we did, it is called one-way ANOVA because you are dealing with only one variable. Similarly, I have shown you how you can do analysis if you have red, yellow, blue and green boxes, and these are the number of boxes sold at different stores. So you can go to data analysis, select the data, check the label in the first row and do the analysis, and you get ANOVA table. So incidentally, in this case also p-value is 0.29. So your confidence level is still maybe close to 0.7. So that's not good enough. 70% confidence is not good enough. So that means color does not play any role in the customer's choice of a cereal box. So sometimes we may have more than one variable. So when we have two variables, we call it two-way ANOVA. With no replicate means there is no repetition of any experiment. So for example, in this case, one variable is detergent, other variable is temperature of the water. So you have 3 levels for detergent and 4 levels of for temperature of water. So we choose ANOVA factor without replication because with detergent A and cold water you have only one data point. Similarly with detergent A and cool you have only one data point. So these numbers could indicate the cleanliness level, and when you analyze this by choosing appropriate values you get an ANOVA table. So in this case you get a source of variation for rows which is temperature and columns which is detergent type, and then the error. So the numbers I have explained you earlier. I have explained you the columns. So this is sum of squares, degrees of freedom, mean square, and F ratio. Now in this case you find p values are very small. So if you do 1 minus 0.01, so you get a confidence level of almost 99%. That's very good. So that means temperature of the water has a role to play on the cleanliness that comes out of this experiment. Similarly, detergent also is important. So whenever we find that a factor is significant, in this case both are significant, then we have to find out what should be the best temperature and what should be the best detergent type. So if you look at the summary table here, and suppose we are talking about cleanliness, lower number means more clean. Then if you look at the average, so hot water provides the lowest average. That means you get the best cleaning quality when the temperature is hot. Similarly, out of the 3 detergent, you can see detergent C provides the lowest value. So that means the best cleanliness you get is by detergent C. So this way we choose the optimum values for the two variables or the two factors. So for factor temperature, hot, and factor detergent, it is C. So we can also get experiments with replicates. So this is an example. Detergent A and temperature cold. We are running the trials not one time but 3 times. And that is true for all combinations. So which means we have a replication of 3. So why we have to have replications? The idea is to have our experiments more repeatable and more reliable. And it will give you ANOVA because we have 2 variables. So first row in this case is the row which is temperature and columns are detergents. And if I go back here you can see rows per sample. We have used 3 because there are 3 replications. And whenever we have 2 variables with replication, we also have an interaction term which is the joint effect of detergent and temperature. That is also given, and within is basically the error. So you have the sum of squares. Now degrees of freedom. For temperature it is 3 because temperature has 4 levels, 1, 2, 3, 4. So 4 minus 1 is 3. Similarly columns, degrees of freedom is 2. So you have 3 detergents, 1, 2 and 3. So 3 minus 1 is 2. To find the joint effect or the interaction, we multiply these two. So interaction degrees of freedom between temperature and detergent is 3 times 2, which is 6. And the total degrees of freedom is 35 because you have 1, 2, 3, up to 12 times 3, 36 data points. So 36 minus 1 is 35. And then from 35 you subtract 3, 2 and 6, you get 24. And then all the calculations are given by Excel. So in this case also you see all the variables and the interaction are significant. So because interaction is significant, so that means we can go back to the table and see which total is the least, because we are talking about the best cleanliness. So in fact I see 5, 5 and 3. So again hot water and detergent C. So that combination gives the best possible outcome. So that will be our optimal combination. Suppose there are three factors A, B and C, and each are at two levels. In this situation you can calculate total number of experiments. A has two levels, so start with 2 multiplied by B has two levels and C has two levels, so total 8. So the general formula is you have levels to the power of factors. So like in this case you can simply say 2 raised to 3 and that will give you 8. So the experiments where we use all possible combinations, like in this case if we run all 8 experiments, so this experiment is called full factorial. So we are running all possible combinations. So these are full factorial experiments. Another example, in this experiment you have three factors again, A, B and C, and for the levels, suppose A has 2, B has 3 and C has 3 levels. So to calculate total number of experiments, so you multiply 2 times 3 times 3. So in this case total possible experiments will be 18. If you conduct all 18 experiments, we have full factorial. Another example, suppose now we have 10 factors or 10 variables to study and levels are 2 each. So you can calculate total possible experiments. In this situation will be 2 raised to 10, like 2 times up to 10 times, which is 1024. So 1024 are a lot of experiments. In an industry, conducting 8 experiments or 18 experiments is still manageable, but 1024 is a lot. So if you take an example, maybe a chemical industry where one experiment can take sometimes a week, then 1024 experiments may take like 20 years to complete. So it will be very, very time consuming and it will be very, very expensive. And also by the time you complete the experiment, things may not be relevant. So how do people conduct experiments in such situations? Dr. Taguchi popularized fractional factorial experiments as a way to reduce the number of experiments needed. So using fractional factorial experiment approach designed by Dr. Taguchi, sometimes you can bring down the number of experiments required from 1024 to just 16. So 16 is something which is still manageable. But one thing you'll notice is if you are not collecting data for all 1024 experiments, then obviously there is some loss of information. But it is still better because at least you are able to conduct an experiment and you are not in a situation where you cannot even complete an experiment like 1024. Although it will be ideal to complete it, but if it is going to take 20 years to complete them, 16 is much better. So Dr. Taguchi is regarded as one of the modern quality gurus and he did a lot of work in this field and he was one of the persons who popularized the method of fractional factorial experiments which has become very useful in several industries where it is employed.